Hi guys, good morning. Oh, yeah, everybody's already there. Very good, very good. Shall we start, guys?
Yes, sir.
So,
Yes. Okay. So yeah, so we have successfully completed all the types of bonds, all the types of theories, different explanations it gave, right? All that. So we started with simple Lewis-Strauss structures, understanding what is sigma bond, what is pi bond, what is overlap. And then we went on to see theory of hybridization. There we went on to see the shapes. Certain things were not explained in Lewis theory. We saw in your the theory of hybridization, VSEPR. And with the help of VSEPR, we even understood the bond angles, how they are varying, right? And we went on to see what are dipole moments, right? And then we went on to see MOT. In that, I had so many things, right? And then today we are going to see all the other types of bonds. Okay, so whichever you are not going to regard as bonds in actual bonds in chemistry, right? So those kind of things you're going to see, right? And before that, I just want to tell you one more thing about MOT, right? So we didn't speak about the magnetic properties, right? I told you that say if I have a compound, right? If I bring a magnet near it, three things can happen, right? So what are the three things? Either the particular molecule can get attracted by the magnet, or say it can repelled by the magnet, or say nothing will happen. No repulsion, neither repulsion nor attraction will happen, right? So how is it happening, and how are you going to find out whether what is going to happen with the help of MOT? All these things we'll see, and then we'll move on to the other types of bonds. Okay, fine. So guys, please understand, uh, the electrons. If I have any charged particle, for example, right? In physics, you'll be studying it in your 12th class, but still, I'm just giving you a gist, right? Any charged particle for that matter, right? Any charged particle for that matter will have some magnetic properties associated with this, right? Or in a better way, right? Any charged particle can behave as a magnet, right? Any charged particle can behave as a magnet. Okay, like how they will behave, all these things. If I go in depth, we'll not be finishing it now. So just I'm putting it in a nutshell, right? Any charged particle, any, I would say, in still more depth, any moving charged particle, right? Any moving charged particle can behave as a magnet. Okay, so obviously that is why, because of these electrons which are there, which are charged and which they are moving, right? I can regard each and every individual electrons as magnets, tiny magnets, small kuti magnets. I'll be able to regard them as. Okay, so obviously depending on how they are and all that, this attraction or repulsion or nothing will happen, like all these things will be taken into account. Okay, fine. So each and everything will have their own magnetic moments. How do you have dipole moment, right? I have something called as magnetic moment. So like, again, we'll not go in depth of it. Like, try to understand that, how to say, the direction in which these magnetic moments are oriented matters here, right? Okay, so anyways, we'll move on to it, right? uh, right. So let me take a molecule. I mean, let me take an atom or or a compound or whatever it is, right? So it is going to have so many number of electrons, isn't it? They're going to have so many number of electrons, and these electrons will be oriented randomly. We will not be able to make sure that okay, it is moving in this direction only. There are going to be so many electrons that are moving in random directions. Okay, so I will represent it like this. Say that I have so many electrons moving in random directions like this. Okay, so these are into each and every arrow mark here represents one electron and in different direction, right? Okay, so what is going to happen is, right, if I apply some magnetic field, external magnetic field, already they're going to behave as magnets, right? And obviously if I'm going to apply some external magnetic field, I'm basically external magnetic field in the sense I'm going to bring in some magnet. That's what I'm trying to do, right? So if I apply some external magnetic field, something is going to happen here, right? Depending on what is that something, right? I told you that if I bring in the magnet, something is going to happen, and depending on what is going to happen, right, I'll be able to predict certain things. Right? I told you what are the things I'm going to predict, right? So the first probability, right, the first possibility, right, what is going to happen is this, right? The first possibility is that now I have the magnetic field, external magnetic field in this direction, right? So what can happen is all these electrons which are here, right, all these electrons which are here can orient themselves in the direction of the magnetic field, right? So you saw what happened here. These are randomly oriented, right? Now when the magnetic field is applied, I see that they are orienting in the direction of the magnetic field, orienting along the direction of the magnetic field, right? So obviously this is what is my attractive force, right? Whenever you see this is happening, right, so you will see that that particular molecule will get attracted by the magnet. Are you able to understand, right? So when the magnetic field is applied in this direction and the electrons are getting oriented themselves in the along the direction of the magnetic field, so this talks about attractive force. That means what? This molecule will be able to get attracted by the magnet. Okay, fine. Now this can again be of two types, right? This can again be of two types. What are the two types? One can be a permanent effect, right? And one can be a temporary effect. What do you mean by permanent and temporary here? So the thing is, if I remove the magnetic field, I'm applying a magnetic field, right? So if I remove this magnetic field, there also what is going to happen is what is we are going to see. The first possibility is after removing the magnetic field, this arrangement can go back to this arrangement. That is, however it was, it can go back to that, right? Or even after removing the magnetic field, they can stay as such, right? Even after removing the magnetic field, they can this arrangement stays, right? So this can be of two types. That is my temporary effect, or it can be a permanent effect. What do you mean by temporary and permanent? Just now I explained. Just after removing the magnetic field, if they're gonna go back to the random arrangement, it is temporary. And even after removing the magnetic field, if you're going to stay as this, it's only it is going to be a permanent effect. Okay. So again, and now I'm going to give the names. This is where it's going to be important, right? So whenever you see there is going to be attraction, or whenever you see the electrons are orienting themselves along the direction of the magnetic field, and if it is temporary, that is, after they remove the magnetic field, they're going to go back to their original position. These kind of molecules are what are called as diamagnetic molecules. Right? These kind of molecules are what are called as diamagnetic molecules or diamagnetic species, they call it. Right? So what are diamagnetic? Diamagnetic species, if I apply magnetic field, they will get attracted by the magnetic field, right? But if I remove the magnetic field, they are going to go back to their random orientation of electrons, right? That is what is called as diamagnetic species. Okay. Now, out of it is like, what am I going to call this? Permanently magnetized species. These are what are called as ferromagnetic species, right? These are what are called as ferromagnetic species. And please understand, these ferromagnetic substances are the one which are used for producing magnets, right? Because you can see that once the magnetic field is applied, like they are going to orient themselves in the direction of the magnetic field. So this kind of material, that is ferromagnetic materials, are the one which are used in preparation of or manufacturing of magnets itself, right? And obviously examples can be iron. Iron is a very good example for this. Nickel, cobalt, all these things which are used in the production of magnets are actually ferromagnetic materials, right? So ferromagnetic materials are permanently magnetized. That's what you need to understand. Okay, fine. So this is one possibility, that is they are orienting themselves in the direction of the magnetic field, right? Now what can be the other possibility? The other possibility can be, if you can take this down, I can drop this part, right? So attractive force, temporary, permanent, diamagnetic and ferromagnetic, right? Good. So if you have taken this down, right, say the next possibility can be, say this is the direction of the magnetic field, right? Now what can happen is the direction of where the electrons are going to orient themselves in the opposite direction of the magnetic field. That means what? They are repelling the magnet, isn't it? Right? So they are orienting themselves along, in the opposite direction of the magnetic field. Now this proves that this is basically my repulsive forces getting into the picture. Right? This is my repulsion. So when I bring the magnet near those kind of molecules, they're going to repel the magnets. Right? Okay. So again, this can be of two types. One can be temporary effect, and one can be a permanent effect. Right? So again, I'm going to give some names. Right? So these kind of substances which are getting repelled by the magnet temporarily, that is what? When I apply the magnetic field, this happens. When I remove the magnetic field, they'll go back to their original position, random arrangement, right? So if you see that happening, these kind of substances are what are called as paramagnetic substances, right? These kind of substances are what are called as paramagnetic substances. Okay, and whenever you have a permanent effect, that is, they are permanently repelling the magnet. Again, these can also be used for producing magnets because this is a permanent effect, right? Okay, so whenever you see this is going to be a permanent effect, that is the permanent repulsion for the magnet, these are what are called as antiferromagnetic substances. These are what are called as antiferromagnetic, exactly, ferromagnetic, antiferromagnetic substances, diamagnetic, paramagnetic. Okay, so this will be able to see, right? There can be one more possibility also. Like we saw, first possibility is complete repulsion. First possibility is complete attraction. Second possibility is complete repulsion. What can be the third possibility? Nothing will happen, isn't it? Now, how are we going to explain this that nothing will happen? So the possibility can be like this. Say I apply the magnetic field in this direction, right? Say there are 4 electrons, assuming. There are 4 electrons, assuming. So what is going to happen is 2 of them are going to orient themselves along the direction of the magnetic field, right? And 2 of them are going to orient themselves in the opposite direction of the magnetic field. Are you able to understand what I'm telling? There are totally 4, assuming there are totally 4 electrons. 2 electrons are going to orient themselves along the direction of the magnetic field, and 2 electrons are going to orient themselves in the opposite direction of the magnetic field. And obviously, what will be the net result? Net result is nothing. No attraction, no repulsion. It is just going to stay there, right? So these kind of there is no permanent or temporary effect here, like because there is actually even like even if I apply magnetic field, nothing is happening. Even if I don't apply magnetic field, it is almost the same because either way, no attraction or no repulsion, right? So these kind of substances are what are called as ferrimagnetic substances, right? Not ferro, it's ferri, right? So these kind of substances are what are called as ferrimagnetic substances, right? So you have to know the terms, people, right? Paramagnetic, first we'll start with diamagnetic, attraction, that is temporary. Ferromagnetic, attraction, permanent. Paramagnetic, repulsion, temporary. Antiferromagnetic, repulsion, permanent, right? And this, nothing happens, it is going to be called as ferrimagnetic substances. Understood? Right. So this is the thing we have to understand. How is it that certain things are getting attracted by the magnet, certain things are getting repelled by the magnet, and certain things nothing is happening, right? Okay, fine, we understood. Now we will not be able to check this. Check like this for every substance. I'll not be able to see the. Apply a magnetic field. I have to see how the electrons are oriented. It is impossible, right? So we have to, by the help of MOT, that is by the help of your molecular orbital theory, right? You will be able to predict whether that particular molecule is paramagnetic or diamagnetic. That can be found out, right? Again, I'm telling, with the help of molecular orbital theory, you will be able to find whether that particular particular molecule is going to be paramagnetic or diamagnetic. But ferromagnetic, antiferromagnetic, ferrimagnetic, those things will not be able to predict. 2 things only we will predict, whether it's going to be a paramagnetic species or whether it's going to be a diamagnetic species, we'll be able to predict, right? So we'll see how are we going to do that. Okay, right? So these are about the different types of magnetic substances. Okay, now very simply I'll put it. Okay, So if you find there are unpaired electrons in any one of the molecular orbitals, right? If you actually, this holds good even if you talk about atomic orbitals, right? So generally what they say is in the atomic orbitals or in the hybrid orbitals or in the molecular orbitals, whatever types of orbitals you have, if you find that there are unpaired electrons, single electron, not paired, right? In an orbital I can have two electrons, right? So if you see that one of the orbital has only one electron, or say two of the orbitals are having only one electron, at least one unpaired. So I would say at least one unpaired electron. If you see, right, now these kind of species will definitely be paramagnetic. Right? These kind of species will definitely be paramagnetic. Okay, right? So how can I give you examples? The best example I can give you is O2, right? So what happens in O2? I know the molecular orbital configuration, so it is 16. So it will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px equal to pi 2py, 2 1 2. So 1 2 3 4 5 6 7, and then pi star 2px equal to pi star 2py, 1 and 1, not two alone here. It should be 1 and 1. Hund's rule of maximum multiplicity, right? So you can easily see that pi star 2px and pi star 2py have unpaired electrons here. Instead of having two electrons, they have only one electron. So definitely O2 is going to be paramagnetic in nature, right? O2 is going to be paramagnetic in nature, right? Very, very simple to find out whether it's going to be paramagnetic or diamagnetic. You just have to write the electronic configuration in terms of molecular orbitals and check whether they have any unpaired electrons. If they have any unpaired electrons, they are going to be called as paramagnetic. And if all the electrons are paired, all paired electrons, then it is going to be called as diamagnetic, right? All the electrons are paired, right? Now, there are no unpaired electrons, then it is going to be called as diamagnetic. Very, very simple. Unpaired electrons, paramagnetic. No unpaired electrons, diamagnetic. Very, very simple. Okay, right? So this is the only thing which we missed in your molecular orbital theory, right? So guys, do you have any doubts in MOT? You wanna ask me anything? Shall we move on?
Yes.
Okay.
No, sir.
Okay, fine, cool. So yeah, we have successfully completed ionic bonds, covalent bonds, in depth, everything is studied. Okay, so now we are going to study the other secondary types of bonds. You see, what are they? Okay, right. So when I started this chapter, I told you that bonds in chemistry can be of two types, right? So one are what are called as primary types of bonds, the other one are what are called as secondary types of bonds, right? So to understand this, we took Dalton's atomic. Okay, I will not tell. You tell me what is the difference between primary and secondary types of bonds?
Sir, primary, there is 100% rearrangement of electronic configuration.
Yeah.
And in secondary, it's partial rearrangement.
Very good, very good. Exactly. That's what I was exactly going to say. Right. So it's all about how the rearrangement in electronic configuration is taking place. Right. So I know in an ionic bond or a covalent bond, the electronic configuration is completely changed in order for me to attain octet or for some other reasons. Right. So I obviously know that the electronic configuration of that particular atom is completely changed. Right. But there can be possibilities where the electron is not completely gone, right? It still stays inside the atom only, but it is little displaced, I would say, right? So as she said, I'm going to have only partial rearrangement of electronic configuration in these kind of bonds, right? So when I say secondary bonds, right? When I say secondary types of bonds in chemistry, as we told, I'm going to have only partial rearrangement of electronic configuration. So what now will come into this? I can have dipole interactions. I'll tell you what are these, don't worry. I have something called as dipole ion interactions. I have beautiful phenomenon of hydrogen bonding. And lastly, I have something called as van der Waals forces. Okay, so this is what we are going to study today, right? Dipole interactions, dipole ion interactions, hydrogen bonding, and van der Waals forces, right? Okay, fine. So we'll see one by one, right? We'll first talk about dipole. Okay. See, we already know what exactly is a dipole. In chemistry, we saw, right? What exactly is a dipole? Guys, can you just recollect and tell me what was a dipole? Not like generally. What do you mean by a dipole?
Equal and
Yeah.
opposite charges separated by some distance.
Exactly, right? It is equal and opposite charges separated by a distance, right? So we saw this dipole when we saw dipole moment, right? And I told you, right, in chemistry, only polar substances can behave as dipole, right? We know what do you mean by polar, right? So there should be some electronegativity difference between the bonding atoms like HCl, HF, H2O, all these things. That I have the OH bond or say the FH bond, all these things are highly polar because I know what is going to happen if it is a HX bond. I know this electron cloud will be more and more towards the more electronegative atom, right? So thereby it is going to induce a partial negative, it is going to induce a partial positive on hydrogen, right? So all these things we already saw. These kind of molecules are what are called as polar molecules. And this exact arrangement which I have here, the del positive, del negative separated by a distance of bond length, this is what is called as my dipole. Okay, fine. Now, this particular, all these things, all the secondary types of bonds have one thing in common, right? What they have in common is it is not like, for example, say if I take covalent bond or an ionic bond, for example, right? They are going to be bonds between two atoms, isn't it? Between one hydrogen atom and another hydrogen atom, I have a covalent bond in H2, right? So now what I'm going to, or say between H2O molecules, there are two covalent bonds, that is two OH bonds, one oxygen atom, another hydrogen atom, one oxygen atom, another hydrogen atom, I have a proper covalent bond, right? Now what we are going to speak is between two water molecules, right? I have one water molecule, another water molecule, what kind of interaction they will have is what are these secondary types of bonds, right? So I would say these are basically your intermolecular forces or intermolecular, okay, we can keep it as intermolecular forces between two molecules, not between atoms, right? Between two separate entities, between two compounds or between two molecules, what is the force? That is what they are, these secondary types of bonds. Between two H2 molecules, between two H2O molecules, between two HF molecules, right? Not between H and F, that is proper covalent bond. Not between O and H, that is again a proper covalent bond. Between H2O and another H2O molecule, what kind of force exists is what are these types of secondary types of bonds. So you would have studied in your lower classes that solids, liquids, and gases. So this thing will have there's something called as intermolecular forces. This is what are these, right? Okay, so we'll move on. So we'll try to understand what is this dipole. So from the name itself, you'll be able to understand, guys, isn't it? Right? Dipole and a dipole are interacting. Dipole, interactive forces, right? So how can I put it? Say if this is one HX, right? So obviously I will say in a beaker, if I say 100 ml of some acid HX, or see, this X can be anything, like assuming that it is some halogen, right? So I will have some millions and millions of molecules in that, say whatever the amount of beaker you have, right? Say there'll be so many molecules. Say I will be able to write it like this. Say again, this will have some del positive. This will have some del negative, right? So now I'm going to speak about the attraction between this individual HX and this individual HX. Now, how will you put the interaction? I have a del positive of the next HX is hydrogen, and I have a del negative of this X in this HX. So I will have an interaction like this, right? I will have an interaction between the del negative of the first X and del positive of the second H, right? So you can see that these two are going to get strongly binded. I have for positive charge, negative charge, they will have a strong force of attraction, right? So this is what is called as your dipole interactions. Okay, right? Now there is another way of seeing this, right? There is another way of seeing this. One way of seeing this is obviously with the help of your del positive and del negative. That is obvious. I will even be able to visualize this particular thing as an attraction between, say, I have HX molecule. Definitely, I'm going to have a del negative, no problem. But say here I have lone pairs, assuming that obviously I know halogens will have some lone pairs, right? Say the next hydrogen is having a del positive. I can have an interaction between this del positive and the lone pairs also, because again, lone pairs electrons are also negatively charged, right? So you can say that it is either going to be attractive force between the del negative and the del positive, or you can even say that the attraction is between the del positive of the hydrogen and the lone pair on the X or the halogen, right? So either way, it means the same. That means there are going to be two dipoles, and there is some attractive force between these two dipoles. Very, very simple. Okay. So please understand that for dipole-dipole interactions to happen, you need to have permanently polar molecules. If you don't have polar molecules, you will not have this charge separation, and definitely you are not going to have this kind of arrangement, right? So you need to have polar molecules. Understood, right? So this is what is my dipole. We are talking about dipole-dipole interactions here. Okay, cool. Hope you got it what I'm saying. Dipole, between them I have an interaction. Then this can be a very big chain. Say I can have one more HX molecule, again having a del positive, again interaction here. Say I can have one more HX molecule having del positive, del negative, again I can have an interaction here. So this can be a very big chain like this, right? So this is how individual molecules are held together. Basically, I know there are going to be so many millions and millions of molecules. How they're able to stay together in the beaker or whatever the vessel is because of these secondary types of bonds, right? How hydrogen atom and oxygen atoms are stay together, that is because of primary bond. But how two H2O molecules are stay together is because of this kind of secondary bonds. Understood, right? Okay. So next we'll move on to dipole ion interactions. Okay, now it's very, very similar to this dipole-dipole interactions only. Okay, but just that as the name tells you, it is going to be an interaction between dipole and an ion. As simple as that, right? Okay, so we'll see what is going to happen. Let me assume it like this. Okay. Okay, I can actually give you the example in H2O, but still, just because now we have, fine. So assume that I have I have NaCl, sodium chloride, right? So this sodium chloride is dissolved in water. Okay, the sodium chloride is dissolved in water. So what is going to happen if NaCl I have in solid? If I add it in water, I know I'm going to form Na plus aqueous plus Cl minus aqueous, right? So the sodium ion and the chloride ion are getting produced once you dissolve them in water, right? So what you see is this Na plus ions and Cl minus ions will be inside the beaker, which contains water, right? Okay, so I know water, the OH bond in water can act as a dipole because it's highly polar, isn't it? So I have a del negative here, del positive here, and del positive here, right? Okay, so obviously now you have the dipole here, right? And you have ions present. So I can say it like this: if at all there is some Na plus, which is here. Now what is going to happen? The del negative of this oxygen and the full positive charge on this ion, that is my positive ion, can have an interaction, right? Same way, if I have a Cl minus here, now this is not a dipole, this is a proper ion, right? Same way, but the del positive of this hydrogen and the Cl minus completely negatively charged chlorine can have some interaction. Same way here also, say Cl minus here, I can have so many interaction, right? So what do you see here? There is an interaction between your dipole and a complete ion. So dipole is the water molecule, and the ions are basically going to be Na plus and Cl minus. Okay, so this is an example for your dipole ion interactions, right? So in a dipole there should be two dipoles. In dipole ion there should be one dipole and there should be one complete ion which is fully positive or fully negative. Understood, right? So hope you got my point, whatever I'm trying to say. This is my dipole ion interactions. Okay, fine, right. Now that's about dipole ion. Now we'll move to the most special or most important of all these, and that is my hydrogen bonding. Okay, fine. So hydrogen bonding is not something very tough to understand and stuff. If you have understood your dipole and dipole ion, hydrogen bonding is actually a special case of this dipole interactions only. Let me put it in that way, right? So let me speak about that. Hope you have taken this down. So we are speaking about hydrogen bonding, which you will even see coming in organic chemistry also. There are going to be so many places where you will be using this. Okay. So I'm telling that hydrogen bonding is a special case of dipole. This is also a dipole interaction only, right? This is also a dipole interaction only, but this is a special case of dipole interactions, right? Involving hydrogens in the picture. Okay, fine. Now to start with this, right? Like I would say that for hydrogen bonding to happen, there should be two conditions which should be satisfied. Okay, so for the conditions are, there should be something called as hydrogen donors, right? There should be something called as hydrogen donors, and there should be something called as hydrogen acceptors, right? For hydrogen bonding to happen, these two things should be there in that particular species. That is, there should be something called as hydrogen donors, and there should be something called as hydrogen acceptors. Now you have to ask me the question of, sir, what is this? Yes. So what do you mean by hydrogen donors, right? So these hydrogen donors are nothing but they are species, they are compounds in which there is a hydrogen atom, right? In which there is a hydrogen atom which is attached to a highly electronegative atom. Very, very simple, right? So hydrogen donors should have an hydrogen atom, right? Hydrogen donors should have a hydrogen atom which is directly attached. I would say this is very important, which is directly attached, right? Which is directly attached to a highly electronegative atom, right? Now, since we are specifically telling it should be highly electronegative, I will be able to tell to which all elements this should be attached. So these highly electronegative elements can only be three, right? So there can be fluorine, oxygen, or nitrogen, right? So whenever you see that there is a hydrogen atom, right? Whenever you see there is a hydrogen atom attached to any of these, fluorine, oxygen, or nitrogen, those kind of molecules can act as hydrogen donors. Okay, those kind of molecules can act as hydrogen donors. So obviously HF molecule, say, or water molecule, right? And I have ammonia. What happens in ammonia? You see there is NH3 and there is direct NH bond. Same way in H2O, I have direct OH bond, and HF, okay, there is a direct HF bond, right? So all these types of molecules where you have this hydrogen atom directly attached to these atoms, any of these three, only and only this. If you see Cl and H, no. If you see some SH bond, no, right? But if you have any of these three, FH or OH or NH bond, right? Now those kind of things can act as hydrogen donors. Okay, fine. Coming to hydrogen acceptors, it's very simple. Hydrogen acceptors, very simple. Now these kind of the only condition is that these kind of molecules should possess lone pairs. These kind of molecules should possess lone pairs. As simple as that, right? So hydrogen donors should have hydrogen atoms attached to any of these three atoms, fluorine, oxygen, nitrogen, and hydrogen acceptor should have some lone pairs. If you have these two, hydrogen bonding is possible. So obviously the interaction, the type of bond or the type of secondary bond which is speaking here is going to be between the hydrogen donor and the hydrogen acceptor, right? Between the hydrogen donor and the hydrogen acceptor, I'm going to have some temporary bond or say a secondary type of bond, that is hydrogen bonding, which is going to get formed here. Okay, now there are species, right? There are species which can act as both hydrogen donors as well as hydrogen acceptors. Okay, so for the best example can be H2O, right? In H2O, what happens? I have an OH bond that acts as hydrogen donor, and I obviously know oxygen atom has a lone pair. Two lone pairs are there on the oxygen atom, isn't it? So obviously there are going to be certain molecules which can act as both hydrogen donors as well as hydrogen acceptor by themselves. Same way with ammonia. In ammonia, what happens? There are three NH bonds on one lone pair on nitrogen. So again, definitely it can also act as both hydrogen donor as well as hydrogen acceptor. Okay. So anyways, so these are the requirements for hydrogen bonding to happen. So we'll see how exactly it happens. There is nothing new to understand. If you have understood your dipole, it is exactly going to be same. So we'll see what happens. We'll take example of water, right? And we'll see how is it happening. Right? So hope you understood the concepts of hydrogen donors and hydrogen acceptors. The time. We have time. Cool. So let me take water molecules. O, H, H. One more H. Right? So I obviously know there is going to be del positive, del negative. Right? Now let me draw one more. I obviously know that oxygen has a lone pair. Two lone pairs are there. Right? Okay. So one more. So this is my, let me put it as a lone pair and say del negative also. Here it's del positive. Now very simple, right? How am I going to explain your hydrogen bonding? As simple as how I explained in your dipole interactions. Del positive, del negative, or say del positive and the lone pair, right? I told you there are two ways of looking at it, right? So either it's going to be del positive, del negative interaction, or you can easily say that there's going to be del positive and a lone pair, which is negative. I can have an interaction there, right? So I can say that I am going to have an interaction here between this del positive of this hydrogen and this oxygen. You see that there is going to be some interaction, right? Same way, I have a del positive here, a lone pair here. Again, I can have an interaction. Are you able to understand what I'm telling? Right? So this is what is called as hydrogen bonding. Right? This is what is called as hydrogen bonding. Right? So you can see that OH bond acts as a hydrogen donor, and since oxygen atom itself is is having a lone pair, it can act as a hydrogen acceptor also. Right? So here one of the water molecule is going to act as a hydrogen donor. The other molecule can act as hydrogen acceptor also. But it is actually both the things are done by both. So in this case, what you see, if this OH bond is acting as hydrogen donor and this oxygen atom is acting as a hydrogen acceptor, right? But you see here what is happening, this OH bond is acting as a hydrogen donor and this oxygen atom is acting as a hydrogen acceptor. Are you able to get what I'm saying, people? Right? Again, I repeat, this OH bond, right? This OH bond is acting as a hydrogen donor because this is what is having H plus, H del plus. And this oxygen atom is going to act as hydrogen acceptor. This is about this hydrogen bond. If I look at this hydrogen bond, right, this OH bond acts as hydrogen donor and this oxygen molecule acts as hydrogen acceptor. This oxygen molecule acts as hydrogen acceptor. Understood? Right? Now, same thing can happen even in ammonia. We'll take, like if you want, we can see that. Say ammonia molecule, del positive, del positive, del positive, and obviously I have a lone pair, right? So if I right, so again I can have a del positive. I can have an interaction between this, that is this hydrogen and the lone pair on this nitrogen, right? Obviously, if I have a lone pair here, I can have an interaction between this and this. I'm not able to show it in a 3D way. So I hope you understand. It will be in 3D. Almost all of them would have been attached with each other with the help of hydrogen bonds. Okay, fine. So this is what is hydrogen bonding. Okay, fine. Now this hydrogen bonding can be of two types. Right? This hydrogen bonding can be of two types. So we'll see what are they. Guys, any doubts here? You want to ask me anything?
No, sir.
Okay, fine. Right. So this hydrogen bonding can be of two types. Right. I have something called as intermolecular hydrogen bonding, and I have something called as intramolecular hydrogen bonding. Right. Intermolecular hydrogen bonding and intramolecular hydrogen bonding. Okay, what are these? Now, as the name tells you, you will be able to understand what do you mean by inter-school competitions, people? What do you mean
Between
by
two schools.
Between different schools.
Oh, wonderful, wonderful. So that's exactly what is here, right? So between two molecules, if I have a hydrogen bonding, just now you saw between two H2O molecules, between two ammonia molecules, all these comes under intermolecular hydrogen bonding between two species, right? Now there can be cases where in one molecule only, I have only one molecule, and inside that molecule itself, hydrogen bonding can happen. Intramolecular means in between your school itself, in between your school students itself, say sports day, what do you do in sports day? Between your colleagues itself, you will be competing. Right? So that is example for intra event, right? Intra-school event, between inside the school. So same way, intramolecular hydrogen bonding means inside that molecule itself, I can have hydrogen bonding. And the example I'm going to give you now, but don't get frightened. Right, sir, what is this and all that? Okay. So this is the example is this. Okay, first, what is this, people?
Benzene.
Benzene, sir.
Okay, yeah, benzene, right? So this is my benzene C6H6 molecule. Okay, so don't worry. If for people who don't know about this, do not worry. You will be studying them in organic chemistry. This is just for me to explain the intramolecular. Okay, fine. So C6H6 in all the corners, I have a hydrogen atom basically, right? But that need not be always the case. Instead of hydrogen atom, I can have some other groups also coming here. Okay, so you know there's something called as functional groups. I can have a OH group. I can have something like say NH3 group. So many things are aldehydes, ketones, carboxylic acids, ethers, esters. So many things are there. So any of them can come here. Okay. Now let me take now please understand that when I have only one substituent, say I have one group here. Okay. And so if I'm going to put the second group also, right? If I'm going to put the second group also, now I have, say, assume that there is OH here, assuming. Right? There is a alcohol. This is not exactly alcohol, it's called phenol, but don't worry, we don't have to go into the details. Anyways, so I have already one group here. Okay, OH group is already present at position 1. This is position 1. Okay, now I can have 3 kinds of positions in which I'll be able to put the second group, right? I can have 3 kinds of positions in which I can have a second group coming. Okay, so what can be the positions? I can actually put it in position 2, or I will be able to put it in position 3, or I will be able to put it in position 4. Now, why am I not talking about this and this position? Because they're also going to be second and third if I come from that side, right? If I come from this side, again, this can be second, this can be third, this can be fourth. So I hope you understand what I'm trying to say. So this side or this side, it is same, but this is fourth. That is understood. Okay, fine. So if you put the second group in the second position, right, it is going to be called as ortho substituted. Okay, I know that it is going to be a little clumsy, but please try to understand. So if I put OH and say one more OH group, or say I put NH2 or whatever it is, I can put NO2 group, whatever it is, I can put some other group, any group. If I say that this is position 1, this is position 2, this is going to be called as ortho substituted. Right? Now, if I put it in 1 and 3, say one OH and another OH, for example. Now, 1, 2, 3, third position, I put the second group. Now, this is going to be called as meta substituted. This is going to be called as meta substituted. And if you put it in the fourth position, say I put some other group, one again OH, if I put, right? Now 1 and 4 are substituted. Now these kind of things are what are called as para substituted. Okay, so 1 and 2 ortho, 1 and 3 meta, 1 and 4 para. Okay, so anyways, these are not important for you now. Nobody's going to ask you questions from this now, at least. Like obviously in 11th annual exam, definitely you'll get because you'll be studying it. But okay, like I am especially interested in this ortho, right? Because I'm talking about intramolecular hydrogen bonding. Like these two will not be in the picture. Okay, just for your information, I told now meta substituted, ortho substituted, and para substituted. Okay, so I am not interested in these two. So I will drop this part. Even if you didn't understand completely, all right, don't worry. Okay, fine. So now this is gone. I don't want to speak about this. I don't want to waste my time here. Right, okay. Let me talk about this. Okay, actually, let me bring it to the center. So I'm going to have OH, right? And say I have NH2. Okay, NH2 is again a group. It's called amines, right? So what do you mean by amines? Ammonia is NH3, isn't it? So one hydrogen atom is removed, and if I put a bulky group like this or any other group like this, it is going to be called as amines. Anyways, we'll not go into the picture details of this. Okay, so let me look at this. So guys, please look at here. Right, I have the OH bond, which can act as a hydrogen donor. I told you, hydrogen atom attached to a highly electronegative atom, right? And obviously here also I have a NH bond, which can act as a hydrogen donor, right? Because again, hydrogen atom is attached to a highly electronegative atom. Okay, now I have to check whether I have hydrogen donor capability, sorry, hydrogen acceptor capabilities. And the condition is that I need to have a lone pair present. Yes, I have a lone pair. I have one lone pair here. I have one lone pair here on this oxygen. And obviously, I have a lone pair here on this nitrogen. Right? So now I can have interactions, isn't it? Now see, I'm not taking two different molecules. In the same molecule only I'm speaking. Right? So I can easily see that this hydrogen and this lone pair can have an interaction. Right? And if I can use some other color, I can show that this lone pair and this hydrogen are having an interaction. Right? So this hydrogen, this lone pair, this hydrogen, this lone pair can be in interaction. The interaction means hydrogen bonding. Right? They are having hydrogen bonds. Now you see, there are no two different molecules. This is not between two molecules, but in the same molecule, since I have hydrogen donor and hydrogen acceptor capabilities acting from different sites. Sorry guys. So yeah, so acting from different sites, right? So this is an example for intramolecular hydrogen bonding, and the examples you saw previously, right? So they are going to be called as intermolecular hydrogen bonding. Understood, right? So now the question is, sir, which is stronger? Right, which one is stronger? Intramolecular is stronger or intermolecular is stronger? So always understand that intermolecular hydrogen bonding is always stronger than intramolecular hydrogen bonding. Right, intermolecular, that is between two molecules, right, is always stronger than in the same molecule. Intramolecular hydrogen bonding. Intermolecular hydrogen bonding is always stronger than intramolecular hydrogen bonding. This you have to know. Right. So everybody understood what do you mean by intermolecular and intramolecular hydrogen bonding, right? Okay. Now, what are all the consequences, right? So because I'm going to have hydrogen bonding in certain molecules, there are going to be so many consequences which are going to be there, right? One such consequence is that, see, I know water molecule is generally a very small molecule, okay? So please understand that when I talk about boiling points and melting points, I know what is boiling point, melting point, the temperature at which that particular liquid gets converted to gas, right? So the thing is, generally, molecules with very high molecular mass, you know what is molecular mass also, right? So molecules with very high molecular mass will generally have very, very high boiling points, okay? But you see, H2O is having a molecular mass of only 18 grams. It's one of the smallest values because one small oxygen atom, two very, very small hydrogen atoms are there. So, like ideally speaking, it should be very easy for us to make H2O water to make H2O water to go to the gaseous phase. That means at very less temperature itself, it should be able to undergo this transition, right? But because I have hydrogen bonding, I have the boiling point to be very high, that is to be 100 degrees Celsius. Right? That is to be 100 degrees Celsius. Okay, fine. Okay. Like this is actually a fascinating fact. How? Okay, we'll see that. Cool. So this is about intermolecular, intramolecular. So we're going to speak about the consequence of your hydrogen bonding. So I will say the consequences of hydrogen bonding. So among this, the first one is my boiling point. Right? Okay. So please understand that whenever you have hydrogen bonding, generally speaking, right? Again, generally speaking, whenever you have hydrogen bonding, the boiling point increases. Right? Whenever you have hydrogen bonding, the boiling point increases. Hydrogen bonding is directly proportional. The amount of hydrogen bonding, the extent of hydrogen bonding is directly proportional to the boiling point, BP. Right? Okay, now first let us try to understand what exactly is happening during the boiling, right? So please understand that there is going to be a liquid phase, right? And that liquid phase is getting converted into gaseous phase, okay? So you need to understand that in liquid phase, the interparticle space, the space between two atoms or two molecules is very small when compared to gaseous phase, which will have very huge distances between the molecules, isn't it? Right? So that is why you're supplying energy basically. Why you are supplying energy during boiling, why you are giving some heat is because you want to make the molecules go far away from each other. It's because you want to make the molecules go far away from each other, and obviously when they're very far away from each other, they will eventually go to the gaseous phase from the liquid phase, isn't it? Right? Now, if at all there are no forces of attraction, like if at all there is only the chemical covalent bonds and ionic bonds, only those if you have, it is very, very, very easy for us to do this conversion because they already have maybe close, but they don't have much force. So it's very easy for me to separate them and make them go to the gaseous phase, right? But if they're very strongly held, right? If these are not atoms, these are two different molecules which are bonded, not bonded, which are having very strong interactions, right? So if this is the case, I obviously have to supply a large amount of energy for me to separate them and increase the distance, and then they have to go into the gaseous phase, right? So I obviously, that's the analogy I can give here also, right? So other than the normal bonds, if I have hydrogen bonding between two molecules, right? Now that is going to make it difficult for the liquid phase to go to the gaseous phase, in terms that you have to supply more and more energy, or in other words, you have to supply higher temperature for the boiling process to happen. Because now I have an extra force. Extra force is what? The hydrogen bonding, right? That is why I say that whenever you have hydrogen bonding, right? So definitely it is going to have increase in boiling point, especially if you have intermolecular hydrogen bonding. We are talking about two molecules hydrogen bonded, not inside the same molecule, right? So whenever you see that intermolecular hydrogen bonding is there, definitely I'm going to have increase in boiling point. Okay, right? Cool. Now look, and okay, for boiling points, what and all are the other criteria, right? For how will you compare the boiling points of different species? Is very simple. Boiling point is generally directly related to the molecular mass. More and more is the molecular mass. More and more will be the boiling point. This reason why this happens, I will tell you when I see Van der Waals forces. Okay, why is it that when I have high molecular mass or atomic mass, that increases the boiling point? I'll tell you the reason when I look at Van der Waals forces, because that is how it can be easily explained. Anyways, so whenever I have hydrogen bond, the boiling point increases. Like, let me take an example. If I consider your methanol with H2O, right? When I consider your methanol with H2O, now look at the molecular masses. It is 12 plus 4, 16, 16 plus 16, 32 grams. Here it is 18 grams. These are the molecular masses. Okay, these are your molecular masses, right? So if you look at the boiling points, right? If you look at the boiling points, here I have 100 degrees Celsius, and it is approximately here only 70 degrees Celsius, right? I told you molecular mass and boiling point should be directly related. So obviously I expect this should have had more boiling point, right? But obviously what I see is H2O is having a boiling point. Okay. Now, what is the reason? The reason is hydrogen bonding for sure. But the thing is, please understand that here this also can have hydrogen bonding. This also can have hydrogen bonding. How hydrogen bonding? Now you see that this OH bond, which is here, can be polar. I have a del H plus here. It can be hydrogen donor, hydrogen atom attached directly to the highly electronegative atom, right? And I obviously have lone pair present on this oxygen also. So this can have hydrogen bonding, no doubt about it. And here also I obviously know that H2O can have hydrogen bonding, right? But now it is all about what is the extent of hydrogen bonding. Where am I going to have more hydrogen bonding is the question, right? In both the things I have oxygen atom, both the oxygen atom have two lone pairs, right? So I would say if I talk in terms of hydrogen acceptor capabilities, right? If I talk in terms of hydrogen acceptor capabilities, both the things are same, because both have oxygen atom which have two lone pairs, right? So what is hydrogen acceptor capability? They should have lone pairs, right? So you have two lone pairs on both the oxygen atom. So hydrogen acceptor capabilities are same, right? But if I look at hydrogen donor capabilities, here you see there is only one hydrogen that can be donated, right? But here you see there are going to be two hydrogen atoms which can act as hydrogen donors. So definitely in H2O, there is going to be more extent of hydrogen bonding than in the case of methanol. And that is why you see the boiling point of H2O is higher and that of methanol is lesser, that is 70 degrees Celsius. Are you able to understand? Now both of them have hydrogen bonding, but the extent of hydrogen bonding in H2O, because it has two hydrogen atoms which can be donated, but ethanol or methanol have only one hydrogen atom which can be donated, right? So the extent of hydrogen bonding is higher for H2O, thereby increasing the boiling point, and this is having lesser boiling point. Clear, right? So that is the first consequence. Or let me look at it like this. If I give you one more example, you will be able to understand. Let me. Okay. Now, if you look at this, I have OH with your say oxygen double bond. Oh, this is my ortho, right? And if I check with para, okay, when I check with para, right, ortho, and this is my para substituted molecules. Okay, so now here I know I have a lone pair on this oxygen, I have a del plus on this hydrogen, I can have an interaction here. Now this is my intramolecular hydrogen bonding, right? So if I write it properly, right, so there is an interaction there between the hydrogen and the oxygen. Oxygen is going to act as hydrogen acceptor, and this hydrogen is going to act as hydrogen donor, right? And this is my intramolecular. Now this definitely cannot be involving an intramolecular because the distance between this hydrogen and this oxygen is very high, right? So I am not going to have a perfect intramolecular hydrogen bonding, but instead I can have a proper intermolecular hydrogen bonding here. Now how will I explain that? Right. So if I write one more molecule, I write it like this. I have an O and a H, and here I have oxygen and a double bond O. Here also oxygen, double bond O. Right. Now you can easily say that there's going to be hydrogen bonding, intermolecular hydrogen bonding, easily. So here I'm going to have an interaction, and here I'm going to have an interaction. So you can see this and this, right? So obviously I have, this is my intermolecular hydrogen bonding, right? And this is my intramolecular hydrogen bonding. And I told you only intermolecular hydrogen bonding helps in increasing the boiling point. So you have same molecular mass. Molecular mass is same because same type of atoms are there. One benzene group, one OH, one NH, one NO2 in both these cases, right? But ortho substituted is having intramolecular and para substituted is having intermolecular. I obviously told you intermolecular is stronger, right? So which is going to have higher boiling point? Definitely your para will have more boiling point than ortho, because in para I have intermolecular, in ortho I have in para I have intermolecular, in ortho I have intramolecular hydrogen bonding, right? So this is going to have higher boiling point compared to this, even though they have same molecular mass, because of the extent of hydrogen bonding, also the type of hydrogen bonding, right? So you see, whenever you have intermolecular hydrogen bonding, the boiling point is increased, right? Because the molecules are very close to each other, very difficult to break them apart, right? That is one thing. What is the time? Okay, we don't have time, guys. So one more thing is there. So you have solubility. We know certain things are more soluble in water, certain things are not, right? So we'll see it why this happens in the next class. Okay, fine. Until then, we'll see. Thank you, guys. We'll meet again.
Thank you, sir.
Thank you, sir.
Thank you.